surface integral of electric field, that is ds, surface integral of electric field over a closed loop is equal to total flux. This is the definition of electric flux. Means surface integral of electric field over a closed loop is equal to total flux threading through the loop. This is the definition of electric flux. So surface integral of electric field over a closed loop is called total flux threading through the loop. It is a scalar quantity. It is a scalar quantity. SI unit of electric flux is Newton per coulomb per meter square. SI unit of electric flux is Newton meter square per coulomb, or Newton meter square per coulomb you can write in simplest form. So this is electric flux definition basically. Now, so let us consider a cylindrical region where the electric field line may be passes across this region. So suppose electric field line is passes through this region. This is the electric field line passes across the cylindrical part. Now there are three surfaces. Like first one is, second one, and this is the curved surface, which one is third surface area. So first draw normal vector or area vector of this surface, that is in this direction ds vector, and at this point the electric field line is entering. So in this case ds vector is anti-parallel to E vector. That's why theta is equal to 180 degree. Now right side area vector is in this way, the direction of area vector ds vector, and electric field lines is towards this area vector. So in this situation or this area, ds vector is parallel to E vector, so theta is equal to 0 degree. Now again area vector in this surface is ds vector, and electric field line is touching towards this way, which is perpendicular to this area vector, that is ds vector, perpendicular to E vector, that is theta is equal to 90 degree. So we have three cases in this. Case 1, ds vector anti-parallel to E vector, so that the angle in between these two, theta is equal to 180 degree. So we have the formula of flux phi is equal to E dot ds. So E ds angle is cos 180 degree, and the value of cos 180 degree is -1, so flux is minus EDS in first cases. Now in second case, the right side of the cylindrical region, now case 2, so just observe right end of the cylinder, ds vector is parallel to E vector. So if two vector is parallel together, so angle in between them is from 0 degree. So what will be the flux in this case? Phi is equal to, we have E dot ds, instead of dot product, E ds cos, and theta is 0 degree. 0 degree cos 0 degree is equal to 1. So in this case the flux will be maximum across this region because area vector is parallel to this region. That's why flux is maximum. Now in third cases, what will be the possibilities of electric flux? So case third, if ds vector is perpendicular to E vector, in this case theta is equal to 90 degree. So can we put phi is equal to E dot ds, instead we write here E ds cos 90 degree. So cos 90 is 0, that's why we put here the value of flux will be completely 0. So in this case the flux will be minimum. Flux will be minimum. So when we have three values introducing regarding the flux, whether it is maximum or whether it is minimum, there will be the three cases arises. So maximum fluxes across the cylindrical region when area vector is parallel to the electric field, and minimum is ds vector anti-parallel to electric field, that is angle in between the area vector and electric field is 180 degree. That's why the negative flux minus EDS, and the zero flux passing through the curved surface of the cylinder. Why this is? Because the curved surface, the area vector in between is 90 degree. That's why the flux within this region will be 0. So we have three cases. Now one thing I would like to discuss, apart from these three cases, the fourth may be possible, like if the area vector is inclined to electric field, then what will be the situation in this case? So suppose we have a region similar to this, but one extended form I would like to discuss. Suppose this line is arising and suppose it is extended, right? Now I would like to cut it here in this way. So the area vector along this region will be from this way, because area vector is always perpendicular to the surface. So ds vector we have, and same way of the electric field line will be passes across this region is like this. So the angle in between the ds vector and E vector is inclined, we would like to discuss here. So listen carefully in this case what we will do. So suppose we have a region, and if I am extend this cylindrical part. Okay, now suppose I would like to sectioning this cylindrical terms inclinedly. So my possibilities to cut them in inclined plane. So the area vector in this case, the area vector will be something like this. So my interest to draw the area vector or something like this. Okay, so in this case, this is the area and this area is perpendicular to this way. Now suppose this is a ds vector. Now again this same electric field line passing across this region. Fine, same electric field line is passing across this region, so that is E vector, which is inclined to the theta ds vector, and angle is it will be either 45 degree, 60 degree, 35 degree, 40 degree, or less than that. So our four cases, if E vector is inclined to ds vector, then phi is equal to E dot ds is equal to E ds cos, either it may be theta, and theta will be 45 degree, 60 degree, 15 degree, etc. So flux will be according to this subtended angle. Fine. So these are the three cases. Interrelates the total flux and their conceptual way. So very important concept. The deal of this concept is very important. Now after this discussion, I would like to connect the similarities related to electric flux, that is Gauss's law. Gauss's law, very important concept. So what does this law indicates mainly? So we would like to discuss, it gives a basic relation between the net electric flux through a closed surface and the charge enclosed by the surface, right? The main thing is it gives the relation between the net electric flux and charge enclosed by the surface. Fine. All right. So basically this is main theme of this law. And one thing is very important, that is the electric field of any system of charges or continuous distribution of charge. Fine. So this is valid for symmetrical surfaces. Now the statement of Gauss law, that is total flux is equal to 1 by epsilon naught times to the total charge enclosed, that is phi is equal to 1 by epsilon naught into q naught, or is equal to E dot ds. So interrelated diagram. First we have a Gaussian surface. Mark Gaussian surface. First is mark, draw Gaussian surface. Draw Gaussian surface. Second is mark ds vector, E vector and theta. Next, total charge enclosed. Total charge enclosed. And then lastly apply Gauss theorem. So suppose we have plus q charge. So first need to draw Gaussian surface of this charge. So Gaussian surface of this charge is like a spherical charge distribution, and the field line is tending outward symmetrically through this spherical region. So this is the electric field line symmetrically distributed across this spherical region. This is the electric field line. Now this one is a Gaussian surface. Which is already I have discussed this remarkable points. First we need to draw Gaussian surface. Then related to this Gaussian surface is basically the radial length of this Gaussian surface is supposed to r. Now mark ds vector. So suppose we have an elemental region or length ds vector at the surface of this spherical region and call as a ds vector, and this ds vector is a area vector which is always perpendicular to the surface. So secondly we would like to draw ds vector. So name of this is ds vector, and ds vector is always perpendicular to the surface. So we have a surface ds vector which is normally outward, and at this point the field line, electric field line, which is also outward. So the point is ds vector is parallel to E vector. That's why the angle in between these two, theta, is equal to 0 degree. Fine. So we have ds vector, E vector and theta in this case, right? So according to this figure we would like to draw like a kulfi. You can say this is a kulfi. Fine. And this region, this diagram is basically distributed along the region of these three-dimensional spherical surfaces. Fine. Now suppose this is the point, we can mark here as a point P. So question is, what will be the electric field magnitude at this point E due to this plus q charges and distances are within. So first we have to decide what is the magnitude of the electric field at this point. Okay, and the charge distributed, total charge enclosed is plus q. Okay, this is a symmetrical surface, and around this symmetrical surface charge is distributed plus q. Fine. So as we all already know that the expressions, the electric field due to point charge, electric field due to point charge, electric field due to point charge plus q at point P. So E is equal to basically 1 by 4 pi epsilon naught charge q divided by r square. Fine. Now, according to the flux, phi is equal to E dot ds. Now the value of this surface is phi is equal to E dot ds, or phi is equal to the surface integral of electric field over a closed loop. So E ds cos 0 degree. Why the cos 0? Because ds vector is parallel to E vector. Fine. So phi is equal to E ds, and already we have the value of 1 by 4 pi epsilon naught, that is E 1 by 4 pi epsilon naught q by r square. The integration of ds, and if open the closed surface, the region will be, or boundary value will be 4 pi r square, that is 1 by 4 pi epsilon naught q by r square, and ds 0 to 4 pi r square, that is phi is equal to 1 by 4 pi epsilon naught q by r square into 4 pi r square. 4 pi cancel out, r square cancel out. Again lastly we have to apply Gauss theorem, that is phi is equal to 1 by epsilon naught times to the total charge threading through the loop. Okay, so remaining part we have phi is equal to q by epsilon naught. This is basically the formula of Gauss law. Fine. So hopefully you got this key points, interrelate the derivations and the connectivity of this topic related to the flux. Fine. Now after this topic we would like to discuss the applications of Gauss law. Okay, thank you for this video. Have a good day all of you.